Good morning, everyone. Thanks for joining us today for this final intern talk by Parthasaarathy Sudarsanam on coding spatial audio. Partha is a PhD student at the University of Tampere. And with that, take it away.
Yeah, thank you. Great. Sorry for the delay, and good morning, everyone, and welcome to my final intern talk. So before I start, I think it's only fair I thank my mentors, Hannes Gamper and Sebastian Braun. Both of them have been very supportive and helpful, and also let me do independent research quite well, and significantly contributed also to this work that I'll be presenting here. So yeah, let's dive into the talk. So the topic of this talk is FOA Tokenizer, learning discrete representations of spatial audio using multichannel VQ-GAN. Slightly longer than my name, I guess. So, but yeah, in essence, all we are trying to convey with this long topic is we are trying to tokenize spatial audio. That's it. So you all know, like these days in LLMs, text is being represented as tokens. All we are trying to do is, okay, you have spatial audio, I want to create tokens out of it. That's it. Okay, so yeah, we will go through the agenda. So I'll briefly introduce what spatial audio is and what is the motivation and problem statement that we are trying to achieve. And then I'll share some related works, and then what we experimented. I'll share some results and insights, and finally also some limitations and what are the future works that's possible. Great. Let's get started with spatial audio. What exactly is this spatial audio? When we say spatial audio, all we say is the feeling of sound coming from all around you. So most of you would have heard or experienced stereo. So you have the feeling of sound coming from left and right. So we don't want to limit ourselves to just this. So we want to cover the entire sphere around you with the sound surrounding you from all directions, just like how we experience sound in real life, right? So for example, our brain and ears, they coordinate into a system where even if you close your eyes, your brain is capable of finding out different sources, where they are coming from, how loud they are, at what distance they are, all these stuff. And basically it uses some small clues like, okay, there is a small difference in time between the sound arriving at your left and right ears. And then there are reflections of your body, reflections of your wall, and then we move, the sources move, and the brain has a sophisticated way of using all this information to create a very immersive experience. So when we say spatial audio, this is what we are trying to achieve. So we also want to create this kind of a immersive listening experience. So for example, many of you have joined this call through Teams. So the goal of spatial audio is making you realize or experience sound the same way as you would if you are sitting here in the lecture hall. Okay, so how do you capture spatial audio? So there are some special Ambisonics microphones which are mounted on some special structures, like a couple shown here. One is a tetrahedral structure, and then one is on a sphere. So you can keep on adding more microphones, each capturing sounds in different directions. And the more microphones you add, of course, you get nice spatial resolution of the sound field around you. But of course, it keeps adding complexity, right? Okay, so now we capture the spatial audio. How do you represent it? So one popular format that's gaining popularity is this Ambisonics format, or especially first order Ambisonics, which is a compact representation of the sound field around us. So basically in FOA format, you have these 4 channels, usually denoted by W, X, Y, and Z. So how I would think of first order Ambisonics, it's we are trying to approximate the sound field around us using some basis functions. So for example, here you can see the basis functions of the first order Ambisonics. So there is this omnidirectional microphone, so that tries to capture sounds from all directions equally. And then you have this 3 figure-of-8 microphones along the 3 Cartesian axes. And then it tries to capture the sound energy from, let's say, the horizontal or the X plane, Y plane, and the Z plane. Okay, so now we have a way to represent spatial audio using this first order Ambisonics. But why do we have to represent with first order Ambisonics? So as I said, one advantage is it is a minimal format. So how I usually imagine FOA is it's like you're trying to approximate a function using, let's say, just the first few terms of a Fourier series or first few terms of a Taylor series. So what you get is a rough estimate of the sound field around you, but it's still a good one to start with. Of course, you have higher order Ambisonics where you get more good spatial resolution in the estimate, but then it adds complexity in processing as well. So FOA is a minimal yet complete format. So that's one advantage why we use FOA. And I think the biggest advantage is it provides rendering flexibility. So if you have spatial audio recorded in FOA format or represented in FOA format, you can basically render it to any kind of loudspeaker array that you have. Could be stereo, surround sound, binaural, whatever. So the thing is, with FOAs, you can finally render sounds in VR, gaming environment where you get this immersive feeling. So that's basically a brief introduction to spatial audio. So then let's get to the motivation of what we wanted to do in this internship. Okay, so our desire was we want to build one framework for this first order ambisonic spatial audio where we desire to unify compression, analysis, and generation of spatial audio. So as I said, FOA is the minimal representation of spatial audio, but still it is high dimensional. You need 4 different channels to represent spatial audio. So of course it's quite expensive to store or transmit in its raw form. And so our goal is we want to build a structured, compact representation using neural networks of this spatial audio. And also we wanted to have a discrete representation of first order ambisonics so that with the discrete tokens, it's also possible to manipulate this and generate new interesting spatial audio. So that leads us to the problem statement that we are interested in. So we wanted to do a self-supervised learning to produce a very strong latent representation of the first order ambisonics. So why self-supervised learning? The thing is it's extremely hard to collect spatial audio and annotate them basically. So we resort to self-supervised learning where you can just use the input as your target and then you can generate as many synthetic first order ambisonics data that you want and then train a strong model. So roughly this is what when we started, this is what we wanted to do. We wanted to build an encoder-decoder architecture that takes in an FOA and then decodes it back. And we have this bottleneck of this latent representation where we hope that this latent representation, which is a very compact representation of the spatial audio, is strong enough so that you can do synthesis, you can do analysis, and this is quite compact that you can also transmit. So suppose we achieve this, what are the things that we could actually use this for? So a couple of examples that I would like to share is, for example, once you have this encoder trained, you can train a small network on top of this latent representation, let's say to design a sound event localization and detection network. So this network basically tells you where the sound sources are, when they are active, what is their direction, how far they are, and so on. Another example could be you could integrate it along with a multimodal LLM. So one of our previous interns also worked on this topic. So for example, you could ask questions to an LLM about a spatial audio. Hey, where is this sound coming from? Or how far is this from? Or you could even ask relationship-based question, how far this sound with respect to some other sound, and so on. And of course, we are also interested in generation. So one way how you could generate spatial audio using this kind of a framework is you encode an input spatial audio, and then you train a small latent modification model along with a condition to modify, hey, move the dog from the left towards the right. And then you use the same decoder now to generate a new scene where you control how you want to modify the spatial audio, for example. So these are some examples of what we envision. Of course, there are much more you could build with such a model. So yeah, once we decided, okay, this is what we want to build, we were looking for, okay, what are the works that people have done in this domain that we could use? So some popular works which work for a single channel audio, not specifically spatial, are these which tokenize audio in general, are these works like SoundStream from Google, I think Encoding is from Meta, and DAC is from a company called Discrete. So these models are very strong, provide very strong representations of single channel audio. And they use this technique called residual vector quantization, where you basically quantize the output embedding from the encoder, but then you always have this quantization errors with these quantizers. So you use another quantizer layer to basically quantize the quantization error, and then you keep doing this as many times as you want, and then until you get a very good representation. There is one more very recent work called WavTokenizer, which also targets mono audio. But the thing is, this uses just a single quantization layer, but still achieves equal performance to the previous models that I shared. So, but the thing is, none of these are designed for handling spatial audio in any way. So when we saw the advantages and disadvantages of each of these, so one striking thing we found with the WavTokenizer is its single quantization layer. So let's say when we want to enable generative models, it's easier to control when you have an audio represented as a sequence of single tokens. If you have a residual vector quantization, then each embedding is now represented already by a sequence of tokens. Then it gets a bit messy on how you can control the generation. So basically, to balance between the generation and analysis task, we thought, okay, let's fix this WavTokenizer and see how we can adapt this to spatial audio. That was the goal. So let's look a bit into how WavTokenizer works, because this is also the framework of our own spatial FOA Tokenizer. So basically, the WavTokenizer is a VQ-VAE framework. So it takes in a single channel audio. It has a downsampling encoder. You get the encoded representations. And then, like in any vector quantization model, now the encoder's output is quantized using a vector quantization, where you map the encoder outputs to the nearest vectors. And then you use these quantized vectors to try and reconstruct the input audio. And this is the simple VQ-VAE framework for autoencoding. And then recently people found it like, okay, just the reconstruction loss is probably just not good enough. We want to add more perceptual quality losses. So they started adding more discriminators. So that compares basically the input signal and the reconstructed signal, and try to ensure that both of them sound as close as possible using these kind of discriminators. So once you start adding discriminators, now this framework just gets the name called VQ-GAN, because you have the generator discriminator framework. So in general, WavTokenizer achieves very impressive compression. So basically 1 second of audio at 24 kilohertz is downsampled to just 75 tokens. So that's an insane 320 times compression. That's 320 samples just represented by just one number. And yeah, like any GAN framework, so this is trained with a combination of the generator and the discriminator losses. So yeah, so again, I'm explaining this in a bit more detail because we also use kind of the same framework. So the generator losses are, of course, the vector quantization loss, and then there is the Mel spectrogram reconstruction loss. And because it's a GAN framework, you also have this adversarial loss and the feature matching loss. So, and for the discriminators themselves, of course, you use the hinge loss to make sure that the discriminator correctly finds out which are the real samples and the reconstructed samples. So yeah, just to make things more interesting, people have started adding more and more discriminators. So we will discuss what kind of discriminators people add. In general, the WavTokenizer encoder is quite simple. It's a strided convolution that tries to downsample, for example, 320 times the resolution. And then there is this vector quantization layer. So with the WavTokenizer, as I said, it just uses a single vector quantization layer with 4096 different vectors. And some interesting things people have come up to make a stable VQ-VAE training is initializing the vectors using a k-means clustering of the encoder's output, just to ensure that the vectors are initialized in a distribution that's similar to the input data, so that it starts training quite well. And then there is always this problem of VQ collapse in VQ-VAEs. So there are some vectors that are used significantly, and then there are the remaining vectors that are just never touched. So one way to encourage the model to use a lot of vectors is you keep track of the vector, the codebook usage, and then when some codes are not used a lot, you just replace them with some other codes just from the encoder's output. So this just motivates the model to use more codebooks. And yeah, one striking difference of this WavTokenizer is its decoder architecture. So if you see any encoder-decoder architecture, in general, it's quite symmetric. So the encoder usually downsamples either with a convolution layer, and then the decoder usually upsamples with a transpose convolution. So, but the WavTokenizer uses a different strategy. So the decoder has a backbone which actually doesn't increase the temporal resolution of the quantized outputs, and then just uses a ISTFT layer at the end of the backbone, which basically upsamples to the required. So basically, if your encoder downsampled it by 320 times, you just use an ISTFT with a hop length of 320 so that you get a similar output at the reconstruction. Yeah, the discriminator setup, as I was explaining just a while ago, people have started using like multiple discriminators so that just one is not enough. So they use, the WavTokenizer specifically uses 3 different discriminators to improve the perceptual quality. One is this multi-period discriminator, which basically compares the time domain output of the input audio and the reconstructed audio. And then you have this multi-resolution discriminator, which basically compares the STFT of the input and the reconstructed audio at multiple scales. And then you also have a complex STFT discriminator. Again, at multiple FFT sizes, it compares how the complex STFT of the input and the reconstructed matches. And yeah, one very important detail, at least from our point of view, was what was the training configuration of the WavTokenizer. It was trained for an insane 2 million steps with a batch size of 320, and they use basically 64 880 gigs GPUs for training. So this was difficult for us to match. So that's why I felt it was so important to include. Okay, so that was the baseline that was trained for single channel audio. So now what? How do we adapt it to 4 channel? So that was our problem, right? So, okay, but before that, where is the data? So we had to create a data set. Of course, as I said, there are not much real data sets for spatial audio, so that, at least that are open source. So we had to resort to simulation. So we simulated 10,000 plus room impulse responses using the image source method. So with 1 microphone position and 64 different source positions. And then we generated basically 2 million recordings of 10 seconds. And there are up to 5 sound sources in each clip, varying from 1 to 5. And these are reverberant, noisy, and overlapping sources. Also, sources can be from the same category. It could be like 2 overlapping speech signals and so on. And one thing I have to mention, which probably I didn't mention in the slide, is we stuck to stationary sources for now. Of course, in real world, you would have moving sources. But in this data set that we generated, for now, the sources are stationary. Okay, so the baseline method. Okay, first we thought, okay, we'll use all our brains and do this. Just instead of single channel audio, just put 4 channel audio as input and output. So basically just change the first convolution layer to accept 4 channels, and then at the decoder do the same, and then just modify the discriminators to accept 4 channel inputs and compare the 2 signals. That's it, nothing much. And everything remains the same. The loss function remains the same, the architecture remains the same, and so on. And yeah, it did train well. I would next like to show some audio samples from this model. I am not sure if you would be able to appreciate the stereo nature of this audio on Teams, but I will definitely share the slides later. So one thing that I should mention is the dataset actually contains a combination of all kinds of sounds. So there could be generic audio sounds, it could contain speech, it could contain music, and each file can also contain the mixture of all these sounds together. So yeah, I would like to play one example from each. So let's start with generic sound. So this was the input audio. Were actually coming from two different directions, but yeah, as I said, later I would share the files. And this is a speech example.
Miss McNeil was killed.
The circumstances have changed since last year.
That was overlapping speech, and this was the reconstruction.
Miss McNeil was killed.
The circumstances have changed since last year.
Of course, you can find some quantization artifacts there. That's quite common.
Last week he was taken to the
It's
hospital.
all about money, money, money.
Last week he was taken to the
It's all
hospital.
about money, money, money.
And then an example for music. This was the reconstruction. Okay, it's nice. It looked really good to listen to, and then we tried to compare the acoustic metrics. For example, we compared the fetched audio distance, which is basically a comparison of how the distribution of the input audio samples and the output audio samples are. So that had a very high similarity, so the distance is quite low. The clap similarity between the input and output files were quite high. The STFT distance is basically the difference in the STFT at different scales, and then same as the mel distance. All this looked quite nice, but then it's spatial audio. We just don't care about not just acoustic quality. We also want to maintain the spatial consistency, right? So if in an audio input the sound was coming from left or upper left or whatever, we want the reconstructed audio to also maintain the same spatial directions. So it did not happen in this baseline method. So although it didn't reflect when you listen to the audio through Teams, but later when you listen, you would appreciate that. So yeah, we tried two different baselines. One was what I showed in the previous file, where we just passed 4-channel input and 4-channel output, that I represent here as this MC VQ-GAN, which is this multi-channel WavTokenizer. But then we thought, hey, why to even do all this? Just pass individual channels to the single channel WavTokenizer and then just reconstruct the single channels and then just combine them, right? It's quite easy, right? So yeah, we also tried to do that, and of course you can see the error metrics here. So the azimuth error basically tells you how off the reconstruction in terms of the horizontal angles were. So for example, this multi-channel WavTokenizer was off by 90 degrees. So if something was on the front left, it was reconstructing it on the front right. So it's almost as good as randomly guessing where the azimuth is. And same goes with the elevation error or the angular error or the lateral error. So the model was trying to reconstruct the acoustic contents well, but then it had no clue how to reconstruct the spatial properties. So yeah, when we first saw this result, it was a bit discouraging, but then yeah, this is our the goal, right? So we could propose something that could improve this. So we wanted to design a new loss function that actually helps this model to retain the spatial properties of the input. So we call this spatial consistency loss, which is basically a direction-aware loss that keeps the source in place. So wherever the source is in the input file, keep it the same in the reconstruction. But how do we do this? So in simple terms, what we try to do is we compare the spatial direction of the reference audio and target audio and try to increase the cosine similarity between them. So we did not just blindly try to increase the cosine similarity because it could be quite noisy. So what we try to do is we find regions where the sources are active, where the intensity of the vectors are high, and then we just use cosine similarity on those time frequency bins basically. So if some part of the space is quite noisy or very diffuse, we just basically mask them. We don't care if the reconstruction actually reconstructs the diffuse part quite well. We just care about directional sources. If there are directional sources in the input, we care if the reconstruction reconstructs this directional source well. Yeah, maybe if I show some equations, maybe it makes things clear. So what we do, at first we calculate the intensity vector of the reference audio, which is the input signal, and then the target audio. So basically intensity vectors give you the sound energy basically flowing in the 3 different directions, right? So what we try to do is we want to increase the similarity between the 2 intensity vectors. So if they are quite similar, that means somehow the direction of the sound energy flowing in the input and output are similar. This would mean that spatial consistency is kind of maintained. But then, as I said, this could be quite noisy. So what we do is we try to create a mask, which is a binary mask, where we just care about time frequency bins which have high energy, and then we care about time frequency bins which are not diffuse. So the goal is just focus on time frequency bins which have sound sources, directional sound sources, and then just don't care about low energy time frequency bins and highly diffuse time frequency bins. So, and then yeah, some bins will have more energy, some bins will have less energy. So we also weight these masked regions with the weight of the energy itself. And then that's it. So we wanted to get a single scalar value for the spatial consistency loss. So all we do is, because we wanted a value for the loss, we do 1 minus the cosine similarity. So that gives a number for the loss. And then we, as I said, we weigh it with the energy of those unmasked bins. And then we take the mean. Yeah. So now it's still the same multi-channel WavTokenizer architecture, but then we add this additional term in the generator, additional loss term in the generator represented by this LSC, which is the spatial consistency loss. So we hope that at least this loss would enable the generator to also care about maintaining the same spatial properties in the input as for the output. Okay, so this is the interesting part. Did this really help? Seems we were lucky, it did help. Okay, we did test across quite many data sets how a model with this spatial consistency loss helps us. So the first test data set that we tried was a in-domain data set. What we mean by in-domain is we basically, yeah.
Those are degrees, right?
Yes, those are degrees. Yeah, thanks for mentioning that. Those are errors in degrees. The first test data set is a in-domain data set, which means it's similar to how the training data was. We again created a separate set of synthetic RARs, but then the sound sources were different. So the sound sources were taken from this data set called Sound Bible. And then again, these sources were also noisy and reverberant. We did bring the azimuth error down to 11 degrees, and then the overall angular error, which is I think the most important metric here, is down to 13.7 degrees. And then we also generated a very easy case with this spatial VCTK dataset, which is basically very clean speech. There is no reverberation, no noise, and then this is just randomly placed at different azimuth and elevations. And then you could see that when there is no reverberation, no noise, the model was able to reconstruct the audio with an angular error as less as 4 degrees. And then we went to one of the difficult cases with this MEIR dataset, which is real recordings of room impulse responses, and then we convolve them with some sound sources. And again, these are noisy, reverberant, and remember that the model has never seen a real room impulse response in its training data. And then on this dataset, the angular error was down to 25%, 25 degrees, sorry. I think a good visualization of how this spatial consistency loss helped would be this graph. So if you see the graphs for the in-domain dataset, so the first bar there shows what happened when we just use this 4-channel input and 4-channel output without any spatial consistency loss. So the angular error was as good as random guess at 87.3 degrees. And then compare it with this 4 times WavTokenizer, which is basically just pass individual channels through the WavTokenizer and reconstruct it. Again, that was around 60 degrees. And when we use this multi-channel VQ-GAN with the spatial consistency loss, denoted by this MC VQ-GAN SC, the angular error drops to 13.76. So you could clearly see the impact of the spatial consistency loss on this in-domain data set. Of course, on out-of-domain data sets, definitely this random guessing models are going to be quite poor. So we did evaluate our own model on this spatial VCTK and MEIR. You could see that when the data set is quite easy, less reverberant, less noisy, it reconstructs quite well the spatial consistency at just 4 degrees of error. And then with real room impulse responses, it's 25 degrees of angular error.
But I think it might be worth noting here also that the 4 times WavTokenizer is also 4 times the data rate.
Yes, right? That's true. 4 times WavTokenizer is 4 times the data rate, because you just encode each individual channel, you get 75 tokens for it, and the second channel goes in, you get a new set of 75 tokens for it. But with our multi-channel VQ-GAN, for all the 4 channels, you get 1 set of 75 tokens. That's true. Yeah. Of course, we could see by numbers that the spatial consistency loss definitely helped our case, but we also wanted to visualize and see what was it actually doing, our spatial consistency loss. So we tried to come up with some visualizations. So this, for example, is a model trained without the spatial consistency loss. On the left, you see the plot of the mean intensity magnitude. So the mean is we just average across the time and frequencies. And then this is a equirectangular projection. So on the x-axis, you have the 180 degrees of the azimuth, and on the the x-axis, you have the 360 degrees of your horizontal azimuth, and then on the y-axis, you have the elevation, 180 degrees of your elevation. So you could see a clear blob on, let's say, around 10 degrees of azimuth and 60 degrees of elevation on the input. And then when the model tries to reconstruct it without any spatial consistency loss, it just places the source somewhere else around, I guess it's 150 degrees on the azimuth and minus 60 degrees on the elevation. So it just randomly places it somewhere. So we tried to compare this with the model that was trained with the spatial consistency loss. So here again, the first plot shows for the input, and then the plot in the middle shows the reconstructed version. So it's the mean intensity magnitude of the reconstructed version. You could see the azimuth and elevation match quite well for the single source. And the plot on the right is the most interesting one, I would say. So this is what our loss tried to focus on. So what our loss tried to do is it tries to mask all regions which have low energy or which are highly diffuse, and then it just keeps unmasked the region where the directional sources are. So it just tells the model, okay, I don't care about all these masked regions, but where the directional sources are, try to keep the cosine similarity between the input and output. So this is how the spatial consistency loss actually helps our model to retain its directional properties. So we also tried to analyze this for an example with 2 sound sources. So again, on the left is the input. You could you could see basically 2 different blobs, one on the left and one on the right in the input. And when the model was trained without the spatial consistency loss, it actually just put both the sound sources on the right. You could just see one bigger blob on the right. So when we trained with the spatial consistency loss, you could now again see 2 clear distinct blobs on the left and right, even in the output. And also when you try to visualize what the loss is trying to do, it again tries to increase the cosine similarity of 2 bright spots, one on the left and one on the right. So yeah, this is what our spatial consistency loss basically does behind the scenes. Of course, we also, although the main contribution is the spatial consistency, we also care about how well the acoustic properties are maintained. Again, we try to evaluate on a series of data sets, and it seems to still preserve the same reconstruction quality as the models that were trained without the spatial consistency loss. So adding this did not create a drop in the acoustic reconstruction quality. And here we also tried to test on a real data set. This last row here represents the STARS 23 data set, which is actually both the impulse responses and sound scenes are captured in real indoor environments. It's basically a real recording of spatial sound. So you could see that it still is able to transfer its knowledge on real world data sets. So yeah, I would also like to play some audio files from this spatial consistency loss. Again, I would highly encourage you to listen to this later when I share the slides, because now you could clearly see how well the spatial properties are maintained in this reconstructed version when you compare it with the audio files that I played previously without the spatial loss.
Partha, what kind of audio is this?
This is binaural.
Okay.
Yeah.
For headphones.
Yes, for headphones. Yeah. Please use headphones when you listen to it. And this is the reconstructed version of it. And this is an example for speech.
Der wichtigste Punkt ist ein sofortiger und dauerhafter Waffenstillstand.
And this is a reconstructed version.
Der wichtigste Punkt ist ein sofortiger und dauerhafter Waffenstillstand.
And this is a combination of generic audio sounds and speech together.
Last week he was taken to the
It's
hospital.
all about money, money, money.
This is the reconstructed version.
Last week he was taken to the
It's
hospital.
all about money, money, money.
Some interesting artifact here with the voice being a little bit robotic. I think that's because of the quantization. And this is a music example. And the reconstructed version. So yeah, overall it does do a quite good job in maintaining the spatial properties of the input back in the reconstructed version. But is it the best model? Are there any limitations? There are quite a few limitations. The one that's bothering us quite a lot is underutilization of the vector quantization codebook entries. So this model, the results that I currently shared, basically just uses 40% of the codebooks. So something close to 1,800 codebooks out of the 4,000 that's available to use. So this is in spite of using all the strategies of k-means initialization, trying to reactivate the dead codes and all that. Yeah, so there is still some work that can be done in this direction, and I think that would definitely improve the acoustic reconstruction quality as well as the spatial properties as well. And yeah, and the second limitation is more of a framework-based limitation. I think any quantization-based framework would have quantization artifacts, and this is an extremely highly compressed model. So 4 channels of 24 kilohertz 1 second audio, that's if you calculate, that's like 96,000 samples, and this is just now represented using like 75 tokens. So that's an insane compression. Of course, you would have compression artifacts as well. Yeah, future works is more in the direction of what I said was possible with this model. Now we have a version of this model trained. What we are trying to do now is use this latent representation and build some sound source localization and detection models and try to see if we can somehow manipulate the latents to enable some kind of spatial audio synthesis. So these are some things that at least the sound source localization and detection is something that I'm currently working on. And I would probably also like to mention that we have at least now one configuration of the WavTokenizer or our WavTokenizer with this spatial consistency loss, where we have been able to achieve like 80% of codebook usage, but it's still in the oven. So maybe in a scientific publication later we could see those numbers, how that improved, or did it improve? I don't know. Yeah. Okay. To conclude, we introduced this FOA Tokenizer, where it's a multi-channel VQ-GAN with this spatial consistency loss that tries to compress spatial audio of 24 kilohertz 1 second into just 75 discrete tokens. Yeah, it does work quite well on even noisy reverberant data. It is able to achieve 14 degrees of angular error, which is quite low. Probably, I think 14 degrees of angular error is not something you can, when you listen to it, probably it's not something you can actually distinguish. I think so. Yeah, we are able to enable a compact representation, and of course, we are building some models on top of this for localization, synthesis, and immersive scene understanding purposes. That's the gist of my 12-week internship here at Microsoft. So I would like to express my thanks to a few people. Of course, it has to start with my mentors, Hannes and Sebastian. Thank you for being very kind and supportive, and thanks to all the other colleagues and team members of the Audio and Acoustic Research Group. And I would also like to thank my fellow interns who have left me alone. Now most of them have left to do this job for me to do this job alone. And yeah, thanks to Ivan as well for keeping the group quite lively, and for all the summer activities, and for the 172 coffees that you got me in the 12 weeks and a few more to go. Yeah, thank you. And yeah, I'm open for questions and discussions. Thanks.
Again, ask the first question before the audience basically reads them. So, excellent work, by the way, and very nice talk. What are potential problems and complications if you want to use a higher order Ambisonics? So first order is a kind of creates a quite fuzzy audio scene. Human perception, you should use 64 channels, 7th order, to be beyond the human accuracy. How do you think this will behave if you just try to use it for 16 or 64 channels?
Great. Probably we could just survive with first order just for analysis purposes. Probably if you just want to find out what sound sources are there and where they are located roughly. But as you said, if you want to create a immersive experience when you want to feel the exact audio, of course we should go for higher order ambisonics. But then with higher order, the complexity now comes in the data itself. So this is already now a struggle to just for the model to try to understand, okay, there are just 4 channels of data, and then there is this relationship between the 3 different directional channels. Now you are going to expand it to, let's say, even second order or third order. Now you have to deal with 9 channels and 16 channels. That already makes it quite difficult for the model to actually understand. So definitely probably with the improvement in deep learning, when we can build nice encoders which can somehow understand the relationship between the channels, or if we can provide some metadata for the model to somehow make the model realize that, okay, try to match the relationship between the channels, then that could possibly enable something like that. Yeah, but the thing is, because there is a lot of shared information, I still think we should be able to achieve quite high compression even in that, ideally. Yeah.
I think on that note, you might actually, can you translate, just to give people a sense, the compression ratio into some like,
okay.
like what are 75 tokens per
So
second?
75 tokens per second basically I think means like 0.9 kilobits per second bandwidth. So that's insanely small for a spatial audio. I would say it's even insanely small for single channel audio, but yeah. So this is extremely high compression, and I'm actually surprised by the quality of results both the original paper and we are able to achieve with such a high compression factor. Yes.
Even did you have a...
I'm just tempted to ask the other question. Okay, we can do the spatial audio representation using the high order ambisonics. How about the channel representation? I have a movie with 7.1 audio channels. Mm-hmm. How you would approach the problem for compression and processing of this set of channels?
Good question. Specifically, yeah, if the loudspeaker configuration is,
Okay, they are standard. They are assuming certain positions of those 7 speakers.
yeah. So yeah, probably I would think if you can also somehow, in those cases, if you can also give the model some information about the geometry of the loudspeakers, or so which basically means how the channels are related to each other. So probably that would help the model to come up with some representation on how each of them are related to each other. But
I would convert them into the Ambisonics representation.
yeah, that makes life easier, right? Just convert to Ambisonics and use the model.
One caveat with 5.1 and 7.1 is that for the current training set, we actually try to emulate a real recording. So the 4 channels simulate an actual sound field recording.
Yeah.
With 5.1 and 7.1, 99% of the content is mixed. So it's
synthetic, exactly.
Synthetic
That's the channel.
engineer deciding this source
where
should
to
be
place.
somewhere over
Yeah,
there. So there is
exactly.
no physical relationship between the recording and the physical reaction.
That's true. Yeah.
And that might throw off the model, because now the model is trained on a simulation of a physical representation. With 7.1 or 5.1, it's basically a question of just
I agree.
your compression.
The channel-based thinking of audio engineers may play a dirty trick to the model.
Yeah.
Yep. That's true.
We have one question on the chat. Christian, you can also unmute if you want to ask it in person. If not, I'll read it.
Okay, so the question is, what is the computational complexity, and is it possible to perform real-time decoding of the token? So the model is still fully convolutional, so it's still possible to design causal convolution so that you could still just try. For example, one of the related works that I shared, which is this encoding model from Meta, they actually have a causal version, so where you can actually start decoding as you receive the tokens. So we did not try it with this WavTokenizer, but I think it's theoretically possible to do real-time decoding as well. Yeah.
And in terms of complexity?
In terms of computational complexity, it's still, I would say, quite a lightweight model compared to the bigger foundation models that you find here. So if my memory is right, this basically uses 12 layers of ResNet kind of convolutional blocks at the decoder as well. So it's not quite computationally heavy in modern times, I would say.
Compared to like an audio codec, probably yes.
Yeah.
Yeah. Heavy for a codec, lightweight for a generative AI model.
Sure.
Yeah.
We have one more. Yeah, that's quite a good question. The question is, what methods can be used to reduce the quantization noise? Can there be a trade-off to increase the number of tokens per second, and how it might affect the spatial accuracy? That's quite a nice question. So one direct way I think we could reduce the quantization noise is by falling back to this residual vector quantization technique. So now you have the quantization error, again quantize the quantization error, and keep doing it for 5 or 6 quantization layers, just like some of the previous works use this residual vector quantization. So that would definitely reduce the quantization error. But again, if you think about using such a model for generative purposes, now there is this series of tokens from 6 different quantizers that represents one encoded embedding. So how do you manipulate those things gets a bit tricky, I think. So that's one reason why we actually thought, okay, it's still fine to stick with a single quantization layer, because it's somewhat easier to control the latent embeddings if you just have one sequence of numbers. Of course, you can increase the number of tokens per second, but one of our experiments that I did try to increase it, but somehow it did not converge quite well. I tried to increase it to 150 tokens per second, just twice the number of tokens. But probably with some hyperparameter tuning, maybe it is possible to get that to work. And then, but will this affect the spatial accuracy? That's a bit hard to say. I think it should not affect. When you say affect, probably also mean can it improve the spatial accuracy? Yeah, of course it can increase the spatial accuracy as well. And one other thing we would ideally want to do is also increase the number of vector codes that we have. Currently, it's just like 4,000 codes. That's pretty small compared to if you think about like modern LLMs that I don't know that their vocab size is like 200K, or I don't know what GPT-5 uses, but something of that. And then we are trying to bring spatial audio and then try to just encode it into 4,000 distinct tokens, which is a bit weird, but yeah, but we could also scale that, and hopefully that also reduces the quantization noise. But the only problem with scaling vector codes currently is they tend to collapse quite a lot to fewer codes. So I think there should be some intelligent way to prevent this mode collapse in vector quantization, and then hopefully, yeah, we should be able to.
That's the first thing to do.
Yeah.
For you to utilize the existing concept.
Yes.
And then to do about anything else.
Yes, that's true. I hope that answered your question.
Yeah, on that topic, the underutilization of
Yeah.
the vectors or the code books, does it make sense to have some of the code books focus specifically on the spatial properties and other parts of it focus on the acoustic reconstruction?
That's quite a good question. Initially, when we were discussing about, okay, how should we go about this, we did also have this idea, okay, can we try to do something like an acoustic encoder that gives you a set of tokens that just helps you to reconstruct the acoustic properties, and then you have a set of tokens for the spatial properties of the audio, and then that gives you a nice flexibility that you can just manipulate the spatial tokens and then try to generate quite nice stuff. But yeah, it's still possible to do that. We should think about a nice way to, because it's not completely disentangled. That's what we kind of discussed. Although even the spatial properties somehow also depend on what kind of acoustic characteristics are there for the sound source. So we did not want to completely disentangle it as well. So somewhere a good trade-off, and then if you are able to neatly disentangle but still somehow maintain the relationship of which direction belongs to which sound source. Especially it becomes hard when you have multiple sound sources and then your spatial encoding just tells you like, okay, there is a sound on the left, there's a sound on the right, and then now you need to find a way to associate, okay, which direction belongs to which sound if it's completely disentangled. So there are those difficulties with that, but that's definitely a direction that I think people would pursue for fine control of spatial properties.
Okay. Any more questions online or in the room? If not, thank you again. Bye.
Thank you.